Well, hello there. Earlier, we looked at how to use limits to calculate instantaneous velocity and how this related to tangent lines. Now that we have a stronger grasp of limits, we'll be taking a deeper look into this and defining the derivative, which is one of the two most powerful tools in calculus. We're going to be focusing on finding the tangent line to the graph of the function here. We did talk before about instantaneous velocities and the slopes of tangent lines, and we saw that they both came from the same process. Today we're going to focus on the slopes of tangent lines just because it's a little bit simpler. Now I've got a diagram here. If you want to copy it down, you can pause the video and do so. But I want to take a look at this. Basically, we have the graph of a function, and I didn't label my axes, so I'm going to go ahead and do that now. Perfect. So we have this graph of a function, and what we really want to know in the end is we want to know the slope of the tangent line at the point P. Now what we saw before was that we can look at the slope of a secant line, which is a line that goes through the graph in two different points, and we can use that to estimate the slope of the tangent line. Now, if we pick, so the point we want is an x value of a, and then we can pick another point that'll have an x value of x, and we can see that the slope of that secant line is going to be rise over run. The rise is the difference in the function values, and the run is x minus a, the difference in the x values. And so the slope is going to be the rise over the run. So the slope of that secant line, I'm going to leave just a little bit of a space here because we're going to add something in a moment, is going to be the rise, which is f of x minus f of a. That's the difference in the function values, over x minus a, the run. And that is the slope of the secant line that we have here going between P and Q. Now, if we want to get a better approximation, we know that we can take a value of Q that's closer to P along the graph. Let's use some different colors. We can pick this point, and we can look at that secant line. We can pick this point. We can look at that secant line. And these are getting closer and closer. And as we've seen before, we know that it's the limit as x approaches a that gives us the slope of the tangent line. So I'm going to put that in here. The limit as x approaches a of this rise over run formula that we have, this gives us the slope of the tangent line. So this gives us the slope of the tangent line. All right. This is hugely important. So I'm going to put it in a box. And this gives us that slope. It also, if we were looking at a position function, this would give us the instantaneous velocity at that moment. And I want to look at an example of that because we want to draw connections both to slope and to instantaneous velocity. So we had looked at a problem earlier where we dropped a ball from the top of the CN tower. And in that example that we looked at before, we had a distance function where the distance s of t that it had fallen was equal to 4.9 t squared. I believe that was in meters, where t was measured in seconds. And let's say we want to figure out the velocity after 5 seconds. So what we really want is we want the velocity when t equals 5. Well, so the velocity, the instantaneous velocity at that time is going to be the limit as x approaches 5 of s of x minus s of 5. I'm taking the formula we have up here, but instead of considering it as slope, we're considering it as instantaneous velocity. And that's going to be over x minus 5. That's because we want to know what's going on at 5 seconds. That's kind of our anchor point. And then the other moment that we're looking at, we want it to get closer and closer to that. So we want this x value to get closer and closer to 5. Now here, let's write that limit again. Never forget your limits. All right, so in the numerator, we've got our s of x is going to be 4.9x squared minus s of 5. That's going to be 4.9 times 5 squared all over x minus 5. Now, in that numerator, we can factor out the 4.9, and that's going to give us 4.9 times x squared minus 5 squared. This is all over x minus 5. Beautiful. And hopefully you're noticing that we've got a difference of squares in the numerator. So this is going to be 4.9 times x plus 5 times x minus 5 all over x minus 5. And of course, we can cancel the factors of x minus 5 in the top and bottom to simplify this expression. So we've got the limit as x approaches 5 of 4.9 times x minus 5, x plus 5. And now we can just substitute in 5 for x, because we've got a continuous function. It's polynomial, it's linear actually. So we've got 4.9 times 5 plus 5. 5 plus 5 is 10, and 4.9 times 10 is 49. And since this is velocity, it'll be meters per second. So after 5 seconds, that ball is going to be moving at a velocity of 49 meters per second. All right, I've got a few more videos of example problems so that we can get practice using these rules of limits that we've learned in the last couple of weeks to evaluate these instantaneous velocities, to figure out these slopes, to make it easier than what we did before, where we had to make tables of values and do a whole bunch of arithmetic calculations, and it was a lot nastier. So now that we are more comfortable with limits, we can calculate these instantaneous velocities and these slopes a lot more easily. And over the course of the next few weeks, we're going to develop tools that will allow us to calculate them even more quickly and simply.